602 sextillion 200 quintillion. I mean, it is just astronomically, almost unfathomably huge, right? But here's the crazy part. In the realm of chemistry, this actually represents the approximate number of molecules sitting in just 2 tiny grams of hydrogen gas.
Now, let's brutally juxtapose that massive figure with the infinitesimally small number you're seeing right now. 0.000, well, you get the idea, eventually ending in 166. This represents the mass of a single hydrogen atom in grams. Think about it. If you actually tried doing basic math, addition, subtraction, or multiplication with numbers this extreme on a standard piece of paper, you wouldn't just run out of ink. It would literally be a recipe for total mathematical chaos. We absolutely need special rules to handle this.
And honestly, that's exactly what we're going to master today. Welcome to This Explainer. I am so thrilled to guide you through this kind of a masterclass on demystifying the sometimes intimidating mathematics of chemistry. We're diving deep into uncertainty in measurement, and we're going to give you the ultimate toolkit to handle both the microscopic and the astronomical with absolute confidence.
Before we can even begin to handle complex math, we have to understand the historical anchors of reality that define our units. History really shows us this relentless pursuit of absolute certainty. Just look back at 1889. Back then, the standard kilogram was defined by an actual, physical platinum-iridium cylinder literally locked in an airtight jar in France. And they chose platinum-iridium because it's super resistant to chemical degradation. Length was similar. It used to be based on physical marks on a metal bar. But here's the catch. Physical objects are imperfect, right? They change. So our need for perfect calibration really pushed us to evolve. Jump to 1960, and we redefined length using the light emitted by a krypton laser. And then, by 1983, we anchored it to a fundamental quantum constant, the exact distance light travels in a vacuum in a tiny, tiny fraction of a second. So we literally went from chunks of metal to the absolute laws of physics.
Scientific notation.
It's time to learn the language of scale so we never have to write out 20 zeros again. The crucial thing here is really just understanding this simple formula. Big N times 10 to the power of little n. Big N is your digit term, and it always has to be between 1.000 and 9.999. Little n is your integer exponent. So if you've got a number like 232.508, you just slide the decimal 2 places to the left, which gives you 2.32508. And because you moved it left, your exponent is a positive 2. On the flip side, if you have a tiny number like 0.00016, you move the decimal 4 places to the right to get 1.6. Making your exponent a negative 4. Make sense?
Now, when you're multiplying or dividing these numbers, it's pretty straightforward. Combine the coefficients, follow basic exponent laws, and you're good. But adding and subtracting, that is exactly where people trip up. Let's imagine we're adding 6.65 times 10 to the 4th and 8.95 times 10 to the 3rd. The absolute unbreakable rule here is that you cannot touch those coefficients until the exponents match perfectly. You literally have to shift that 10 to the 3rd to become 10 to the 4th. That turns your 8.95 into 0.895. And only once both are sitting pretty at 10 to the 4th can you safely add them together.
Now that we've got a handle on the math side of things, let's move to Section 3, Precision and Accuracy.
This is where we establish the actual rules of engagement for handling experimental uncertainty. There's this classic confusion between these two terms, but I promise you they are not synonyms. Every measurement has some level of uncertainty based on your instruments and, well, your own human skill. Imagine weighing something on a standard platform balance and getting 9.4 grams. That 4 is basically an estimate. Now weigh that same thing on a highly sensitive analytical balance, and you get 9.4213 grams. See how the level of certainty completely changes? Precision is simply how close your various measurements are to each other, regardless of whether they're actually right. Accuracy, on the other hand, is how close your measurement is to the actual true value.
Let's actually see this concept in action with a concrete experiment. Say the true weight of an object is exactly 2.00 grams. Student A weighs it and gets 1.95 and 1.93. Now those numbers are very close to each other, so they're precise, but they're a bit far from 2.00, so they are not accurate. Then we have student B, who gets 1.94 and 2.05. Not close to each other, and definitely not close to the truth, so neither precise nor accurate. Finally, student C gets 2.01 and 1.99, which averages perfectly to 2.000. And that right there is the gold standard, both highly precise and perfectly accurate.
To communicate all this precision mathematically, we rely on significant figures. There are 5 foundational rules here that you really need to lock into your memory because they dictate exactly what digits are absolutely certain and which ones are just estimates. Ready? First, all non-zero digits count. Easy enough. Second, leading zeros, the ones before the first actual number, they do not count. They're really just there to position the decimal. Third, captive zeros, the ones trapped between non-zero digits, those definitely count. Fourth, trailing zeros at the very end of a decimal count too. And finally, exact numbers, like physically counting 20 eggs, have infinite significant figures because there's absolutely zero uncertainty there.
It's time to shift from just identifying the rules to actually using them in high-stakes calculations. First up, addition and subtraction. The rule here is super specific. Your final answer cannot have more digits to the right of the decimal point than the original number with the least decimal places. Basically, in addition and subtraction, it's the decimal places that dictate our mathematical limits, not the total number of significant figures in the whole number. It's all about how far past the dot you're allowed to go.
Now contrast that with multiplication and division because the rules here are entirely different. In this case, your result must have no more significant figures than the measurement with the fewest significant figures overall. For example, let's say you multiply 2.5, which has 2 sig figs, by 1.25. Your calculator is going to enthusiastically spit out 3.125, but you can't keep that. Your weakest link in that equation was 2.5 with its 2 sig figs, so you have to severely cut your answer down to match, making it just 3.1.
And how exactly do we cut down that number? Well, we use the rounding rules you see here. Honestly, most of this is pretty intuitive. If the rightmost digit you're removing is greater than 5, you round the preceding digit up. If it's less than 5, you just leave it alone. But pay really close attention to the tricky rule for what to do when a number ends in exactly 5. This is a big one. If the digit before the 5 is even, you leave it perfectly unchanged. So 6.25 just rounds to 6.2. But if the digit before the 5 is odd, you increase it by 1, meaning 6.35 rounds up to 6.4. It's a subtle rule, but absolutely crucial.
Dimensional analysis. This right here gives you the ultimate bridge to traverse completely different measurement systems without making a critical error. Sometimes called the factor label method, dimensional analysis is all about converting units by multiplying by unit factors that are exactly equal to 1. Think about it. Because 1 inch is precisely equal to 2.54 centimeters, putting one over the other as a fraction just equals 1. And since a unit factor equals 1, multiplying your data by it changes the unit's physical label without ever altering the actual physical quantity of the object.
Let's see how this builds into a really epic time conversion chain. Imagine you're calculating exactly how many seconds are in 2 days. Step 1. Establish your truths. 1 day is 24 hours, 1 hour is 60 minutes, 1 minute is 60 seconds. Step 2. Instead of doing multiple disjointed math problems, you set up a single unit factor chain, just multiplying 2 days by these fractions. And step 3 is really where the magic happens. Setting up the math in a single step like this allows the hours and minutes in the numerators and denominators to gracefully cancel each other out. Just cross them off. All that's left standing at the end is the exact unit you want, seconds.
Wow, we have covered a lot of ground today, haven't we? Turning these massive abstractions into manageable, precise realities. So as we wrap up, I want to leave you with a bit of a provocative thought. If you took your smartphone out of your pocket right now and weighed it on an analytical balance, how many of those decimal places, how many of those significant figures would actually matter for the math of the real universe? I challenge you to take this toolkit off the screen today. Look at the physical objects in your own hands and really think about the structural rules of reality that define them. Thank you so much for joining me on this explainer, and keep questioning your measurements.